You ever just look around and wonder what the world is fundamentally made of? I'm not talking about the obvious stuff like rocks and water, but everything. The air you're breathing, the device you're watching this on, even you. Well, guess what? There's a code, a fundamental language that writes the story of the entire universe. And that language is chemistry. So let's jump in and start decoding it.
Think about it. On one side, you've got chemistry working on a massive scale to give us clean, safe drinking water for entire cities. And on the other, it's the magic inside the battery that's literally powering the device you're holding right now. It's the science of nature and technology, the simple and the incredibly complex. It's happening all around us and inside of us every single second.
Okay, so what is chemistry really? At its heart, it's actually pretty simple. The source material puts it perfectly. It's the science that looks at all the stuff in the universe, and just as importantly, the changes that stuff can go through. It's the science of what stuff is and what that stuff can become. That's it.
And where do we see it in action? It's everywhere. You've got forensic chemists using it to solve crimes, doctors using it to create life-saving medicines. It's behind the scenes in our rechargeable batteries, our clean water, and even the plastics we use every day. So yeah, this isn't just some boring textbook stuff. It is literally the engine of our modern world.
All right, to really wrap our heads around this, we've got to zoom in, like way in. We need to start with the biggest, most fundamental question there is. What are the basic ingredients of our universe? What is all this stuff actually made of?
So that stuff I keep talking about, the scientific word for it is matter. It's a super simple concept. If it has mass and takes up space, it's matter. From the biggest galaxy you can imagine right down to the phone in your hand, if it has some heft to it and has volume, it's matter. It's the physical substance of, well, everything.
And here's what's so cool about matter. The same stuff can exist in totally different forms or states. Just think about water, right? You've got solid ice, liquid water, and steam, which is a gas. Now, the key thing to get here is that the H2O molecules are still H2O molecules. Nothing's changed about them. The only thing that's different is how much energy they have and how they're all arranged.
This table right here, it just breaks it all down so nicely. Gases, right? Their particles are all spread out, zipping all over the place. That's why they have low density and you can squish them so easily. Solids, on the other hand, have their particles packed in super tight. They're dense, you can't compress them, and they definitely can't flow. And liquids, they're that cool middle ground. The particles are packed in so they're dense, but they can still slide past each other. They can flow.
Okay, so let's break down matter even further. At its purest, it comes in two basic flavors, elements and compounds. I love this analogy. Think of elements as the letters of the alphabet, like O for oxygen or C for carbon. You just can't break them down any further. Compounds, then, are the words you make with those letters. You take two H's and one O. You get H2O, water. And get this, water is absolutely nothing like the hydrogen and oxygen it's made from. It's a totally new thing. Okay, so if elements are the letters, what makes an A and a B a B? To find that out, we have to zoom in one more time. Right past the matter, past the element, down to the ultimate building block, the atom. This right here. This is the question that kept scientists up at night for centuries. If you take a chunk of pure gold and you cut it in half, and then in half again, and you just keep going, what is the absolute smallest, most microscopic piece you could possibly have that is still, without a doubt, gold? The answer, of course, is the atom. But our idea of what an atom looks like has really changed a lot over the years. First, Dalton thought it was just a tiny, solid marble. Then Rutherford comes along and finds this dense, positive center, the nucleus. And then Bohr gives us that classic picture we all know from school, with electrons orbiting like little planets. The point is, our understanding just keeps getting better and better.
So today's model has three main players on the team. In the middle, in the nucleus, you've got your positive protons and your neutral, no charge, neutrons. And then whipping around the outside in a kind of cloud are the tiny negative electrons. It's that classic opposites attract thing. The positive protons pull on the negative electrons, and that's what holds the whole atom together. Simple as that.
Okay, if you remember one thing from this whole explainer, let it be this. You can change the number of neutrons in an atom. That's fine. You can change the number of electrons. No problem. But the instant you change the number of protons, you have a completely different element. Period. 6 protons? That's carbon. Always. 7 protons? That's nitrogen. Always. The proton count is the atom's unique ID. It's its fingerprint. It is everything.
So we've got more than 100 of these elements, each with its own unique proton count. How in the world do we organize all of that? Well, we turn to what is, honestly, one of the most brilliant and powerful tools ever invented in science. Behold, the periodic table. And look, I know it can look a little intimidating, but don't worry, this is not a list you have to memorize. Think of it like a map, or even better, a cheat sheet for the entire universe. And the way it's organized is just, it's genius.
And reading this map is actually pretty easy once you know the basics. The rows going across, those are called periods. As you move along a period, the properties change in a really predictable way. The columns going down are called groups. And here's the really cool part. Everything in the same column, in the same group, behaves in a really similar way. They're like a little chemical family.
But the real magic of the table isn't just how it organizes things. It's that it can predict things. For example, take the size of the atoms. Just by looking at the table, we know that atoms tend to get smaller as you go from left to right, and they get bigger as you go down a column. It's just an incredibly elegant system, isn't it?
Okay, so we have our atomic building blocks, and we have the periodic table, which is our blueprint. But what's the next step? How do these individual atoms actually stick together to make everything else? How does the cosmic glue work?
The answer, it turns out, is all about the electrons. Specifically, the ones on the outermost shell. You see, atoms, they kind of just want to be happy. They want to be stable. And for most of them, happy means having a full outer shell of 8 electrons. This is called the octet rule, and it's the driving force behind almost all of chemistry. Atoms will do pretty much anything, give, take, share, to get that stable set of 8.
And that desperate need for stability is what causes chemical bonds to form. And they do it in 2 main ways. On one side, you've got an atom that just gives an electron away completely. On the other side, you've got atoms that decide to cooperate and share. It really boils down to that, transferring versus sharing.
Let's talk about that first one. It's called an ionic bond. This is the give and take of the chemical world. Think about table salt, sodium, and chlorine. Sodium has one lonely electron in its outer shell that it's dying to get rid of. And chlorine, it's just one electron short of a perfect 8, so it's a perfect match. Sodium gives its electron to chlorine. Now sodium is positive, chlorine is negative, and boom, opposites attract. They stick together like little magnets.
All right, the other way to do it is with a covalent bond. This is more of a partnership. Let's take 2 oxygen atoms, like in the air we breathe. Neither one of them is willing to just give away its electrons, but they both need more to be happy. So what do? They compromise. They agree to share some electrons with each other. And this sharing, this covalent bonding, is the glue that holds together most of the molecules in you, me, and pretty much everything around us. So when you take a step back and look at the whole picture, it's beautiful. Think about it. You've got just over 100 atomic letters, the elements. You've got a few simple grammar rules, how they bond together. And with that tiny toolkit, the entire story of the universe is written. From the biggest star to the smallest cell. It's all just chemistry.
And that just makes you wonder, doesn't it? We have figured out how to read this cosmic code, and now we're learning how to write with it, creating brand new medicines, amazing new materials, new technologies. So the real question is, what's next? If atoms are the letters and bonds are the grammar, what kind of story are we going to write next?